for acid and base unit, then most important thing is like you have to realize some of the chemical they're actually are acid, some of it they're actually bases. Then obviously some common example of acid will be something that you learned before, just like ACL, nitric acid, and sulfur acid. And then I would say this three will be a most important strong acid that we have to learn. And then within most of the time, if you are seeing some other acid that not this three, then technically they are weak acid. And common type of weak acid in within is similar to the formula here, HNO2, H2SO3. Even the formula is like quite similar to here, but then these two are already weak acid. And also carbonic acid, then phosphoric acid. So here's like all kind of a common thing for inorganic acid. And then for organic acid, in within just most of the time COH and in any length of the carbon chain, but then once they have COH, then it's still weak acid. And also phenol. Once you learn benzene and aromatic chemistry, then you will learn one thing is like phenol is kind of a slightly acidic substance because they get neutralized by soda hydroxide. So even though they are not really acidic as carbonic acid, then technically they are still considered as a weak acid thing, because in the structure they have an OH in here, and then this hydrogen can be removes it and then form it as a H plus. Then technically I can still call phenol as also an example of acid. And obviously we have to know how to write down the association equation for both acid and base. And within for acid, there's actually two different versions. You can use in this one obviously, which is a kind of a real version which represented the real formula of H plus. Instead of just using H plus, you have to technically using H real plus to be more precise. And in here, if we put in water, then you will see H real plus will form the enzyme. But if you remove the water, then you can write down this one. Then technically this equation is also correct in the real exam. But the difference is in here you remove the water. So in here you just write down H plus instead of H real plus. But in this equation, then you have four chemical. Then every time you have four chemical, then actually you can break down into two different combination. Because if we look at the acid CH3COH, after that it becomes a CH3CO minus. So it's like donating to H plus, and donate H plus is equal to donate to proton. Because we will consider hydrogen as like one proton and one electron. So if there's only H plus, so it's just equal to one proton. That's why if they're donating H plus ions, then it's equal to donating proton. Then people call it Bronsted Lowry acid, which is a common acid-base theory that we were using in chemistry, especially for acid-base chemistry, for calculation thing. And then after they form CH3CO minus, then technically people will call this one as a conjugated base. Whenever you have acid, and then whenever they don't remove the proton, then the thing that they form, the species they form, people will call it base, and the conjugate base of CH3COH. Because if you talk about in a reverse reaction, you make this one into here, then CH3CO minus have to gain one proton in order to form the COH. That's why technically they're base, because it fulfills the definition which is accepted proton for Bronsted base. It means at the same time, if COH as an acid, then another reaction for water, then which is the opposite direction, because proton donated from COH are going to accepted by water. That's why water accept proton and it gives you H3PO plus. Therefore here will be another combination of acid and base. Therefore in here I would say whenever you have four things in the acid base, the association equation, then you must have two acid and two base. And also at the same time there will be one and two different conjugate pair. When something can be as a conjugate pair, important criteria is like the only different for one proton only. So they may donate or accept to form the opposite chemical. That's why you can see the difference in the formula is only by one proton. And then we can go back and then we'll move on to the association of base. And here's like example of a weak base. And then other than ammonia, methane, or the amine, no matter they have NH2 or like 1H, or they may have even the tertiary amine or primary amine, or even like secondary amine, but they may be having a longer chain. Then it's not really important. They may be like more basic or less basic, but then just in most of the content, most of the syllabus, most of the AFO chemistry syllabus, we don't have to consider which is more basic or less basic, but then just at least all of it are basic. And then maybe the reason for all the amine are basic, and then maybe just similar to ammonia, they have a nitrogen, and more important is like every nitrogen here only form 3 bonds. So every nitrogen here, same as ammonia, they actually have a lone pair electrons. So they're having a lone pair electron, which is kind of a negative things. Then they can easily accept a proton, because proton is actually something that without any electrons. So if you need to accept a proton, then actually you have to form a bond in order to accept the proton. Then how to form a bond with the protons? Then you have to use in your own electron to connect with the proton. That's why the lone pair electron will be quite an important characteristic in here. And you can see when ammonia dissociate, ammonia can accept proton and then give you one more H and 1 plus. That's why you can see the change is different by 1 proton. Ammonia will become NH4 plus. And then in the dissociation of the weak base, then every time in here you have to write down the water. Because if you mix all the water, then you can't form any OH ions. So every dissociation for weak base, no matter the ammonia or amines, then the water is necessary. But then just once they accept a proton, you just put the extra proton connected to the nitrogen. That's why NH2 will become NH3 and 1 plus. That means the carbon, no matter the CH3 or CH2, you just keep on to having a CH3 and CH2. The only variable, the only change is like making one more hydrogen bonded to the N, bonded to the amine, because only the N will have lone pair electrons. That's why in here the equation will be like that. Even the like maybe tertiary amine, maybe something like that, then after you add a proton, after you add the water, then the extra proton will still bond it to the nitrogen, and they make it become a positive ions. So all the time you can see it, the change is like increasing 1 more H and increasing the charge from neutral to 1 plus. That's all the association of the weak base. And then for weak base, the association equation will be like kind of an important one, because for most of the curriculum, you don't have to learn how to calculate for weak base. Most of it just need to know, okay, some of it are like base, and then some of it are weak base, and then for like really precise, you have to know how to write an equation of the weak base. But then in the detailed calculation, is not required in the most of the example, but then not for Edexcel, and also if you're taking RP chemistry, then the calculation for weak base are still important. And then if no need to calculate the weak thing, then maybe calculation for strong substance will be kind of an important task for every student. But then just for calculating strong thing, an important hint is you can make the concentration of acid just directly equal to the concentration of H plus, because they're fully dissociated, they're 100% iodized. That means if you have 0.1 mole per dm cube of HCl, then directly you have 0.1 mole per dm cube of H plus. And then a similar idea if you're referring a strong base. If you have 0.2 of NaOH, then you already have 0.2 concentration of OH ions, because both strong acid and strong base, they will fully associate. So the amounts of the acid and alkali will directly equal to the amounts of H plus and OH directly. And then to solve the pH ratio, which is the most important calculation in this unit, then what you have to do is just pH, remember one thing is like equal to minus log H plus. That means if you have a 0.1 here already, then the pH is directly equal to minus log 0.1. So it's 1 already. So if you think P is kind of a mathematical meaning, what you have to do is just minus log the concentration. And pH, that's why you minus log concentration of H plus. Then if you have OH, then what you have to do is just a similar thing, but then just if you minus log OH, it gives you a 1 also, but then that value is not pH, is equal to POH. Then to change back into pH, then we have to make this value into a new equation, which is called pH plus POH equal to 14. And then for this one, we'll talk about the reason why you have this equation later, but then just at this moment, you may just assume that you memorize this equation first. So if he has 1, then directly we can solve the pH. It should be equal to 13. That's why it's already a kind of a high pH for a strong alkali. Then other than some basic skill for calculation, another special requirement in here is only for IB chemistry only, which is a meaning for reading for amphiprotic. Because maybe for a previous topic for periodicity, topic 3, then you already learned something that's like amphoteric, which is aluminum oxide, for something that can be acid base. But then just here is amphiprotic, so more precisely amphoteric, so it's referring proton. So not just being as an acid base, has to be a Bronsted Lowry acid base. That means they would donate and accept proton. So it's kind of a specific requirement. So therefore, water is a kind of example for something as an amphiprotic, and you can see they can accept proton to form H3O plus. They can donate proton to form OH minus. That's why I would say water is an amphiprotic substance. But it just at the same time, every amphiprotic substance are amphoteric. Because you may think amphoteric just refer any definition of acid base. So that's why amphoteric is like kind of a really big circle. And inside this big circle, just one of the variation here is referring amphiprotic, which is only specific for proton only. That's why for something that are amphiprotic, they must be amphoteric. But at the same time, if something is amphoteric, just like Al2O3, they are not amphiprotic.